And then I have the privilege to introduce the Edith and Peter O'Donnell Award recipients in the physical sciences, Dr. Shengqian Ma. Dr. Ma is a professor and the Welch Chair in Chemistry at the University of North Texas.
Thank you.
Please.
Thank you. Thank you. First of all, it's really my great honor to receive the 2024 O'Donnell Award in Physical Science. I really appreciate the generous support from O'Donnell Foundation. Today I'm going to talk about some of our research in nanospace engineering for sustainability. I do have a video. I don't know whether I can show it, so we have to click the video. Oh yeah, okay, great.
Space, the final frontier. These are the voyages of the Starship Enterprise. Its continuing mission:
to explore strange new worlds, to seek out new life and new civilizations.
Yeah, I think probably most of you have watched this very famous television series for the Star Trek. Indeed, oh, sorry. This is preamble for this television series. It captures not only the challenge encountered in space travel, which is mainly driven by NASA. We have a great talk in the morning, but also capture the challenges in the porous material research. That's about 20 years ago when I was still an undergraduate student. How to control this size, shape, and the uniformity of the porous space. Nowadays, with the 20 years development, all kind of challenges actually have been solved. Now there come a lot of new opportunities to apply the porous materials for all kinds of applications. I'd like to give a brief introduction, for the evolution of the porous materials. The most used porous materials are actually carbons, which are closely related to our daily life. We use it for water treatment. Of course, the other very important porous materials are zeolites, which are particularly important for Texas because we need to use it for oil refinery. And also they came out the mesoporosilicon materials that are very useful for drug delivery. Okay, the last 20 years there emerged some new types of porous materials. One is based upon the coordination chemistry. We call it metal organic frameworks, COFs. The other type is based upon organic covalent bond. We call it porous organic polymer materials. And today I'm going to talk about the porous organic porous materials for sustainability applications. So what are the POPs? Actually, they're polymers, but with some porosity. It's like the plastic, right? So if they have, they're crystalline, we call them COF. Like this, the COF18. Most of them actually are amorphous, but they still have a lot of porosity. Like this very famous the PAF1. Why this type of porous materials are so unique? Because they have very high surface area. So the highest one can reach, 1 gram of the material can reach, the surface area can be as large as the AT&T Stadium soccer field, which we're now going to host the World Cup games in 2026, right? 1 gram of material. So, and also they can be functionalized and very stable for all kinds of applications. So, yeah, I think sustainability is still a topic for 21st century. This includes resource recovery and water treatment, and also air purification. The research, part of research in my lab is we're trying to engineer in the nanospace of the POPs, including water decontamination and to recycle some precious metal and also extract some useful metal sources from ocean and from the brine. So what stimulated me for the water-related research is, the oil spill back in 2010, in Gulf of Mexico. So we're thinking about what type of material we can design to clean up the oil spill. So of course we need to have some, specific properties like high water stability and also high surface area with, hydrophobicity, and also they can be processable. So then we come up to design a material which we can, clean up the oil spill. That's the stimulation for my research. So then we come up to design this, we call it cuff material. We just functionalize with a little bit of the fluoride alkyl chain, make it super hydrophobic. Then we can absorb a lot of oil molecules. Also, this type of material can be easily processable. We can spread it on the, all kind of papers or substrate. Also, we can institute coating, right? Actually, as a husband, okay, one of the job I've been doing luckily, okay, over the last 20 years is to wash dishes after dinner every day, okay, using this hydrophilic melamine. Then we're thinking about, can we make this hydrophilic melamine foam super hydrophobic? Then we can absorb all kind of oil, right? So then this is what we did. We just institute to coat it a little bit less than 2% of our material. We make it super hydrophobic. Then we can absorb a lot of, organic materials. Nitrobenzene is heavier than the water. And make it 1 gram of our material can absorb over 100 grams. 1 gram of this melamine, our material functionalized foam can absorb 100 grams, 100 times. It's huge absorption capacity. And also have a video to show. Could you help me to push the video? This is show the how our material functionalized melamine foam can absorb the oil underneath the water. This shows it doesn't absorb any water at all. Okay, besides doing this oil spill, so we think about to my group, okay, can we do more? There are a lot of other contaminants in the water, right? One of the issue is the heavy metal as represented by mercury. About 30% of the mercury is from human activities, actually, what kind of, the mercury when they emit in the ecological system, they're going to deposit to the fresh water and to form some methyl organic mercury. This is very toxic, we know that. Even this is the recent data we got, in Dallas DFW area. The EPA standard for drinking water is 2 ppb. Actually, in DFW, a lot of lakes, the surface water, the mercury concentration actually is pretty high. Some of them over 300 ppb, some of them over 200 is far above the drinking water. We cannot directly drinking the water from Loose Lake. So then we're thinking about, we need to design some new materials to combat the mercury pollution. So one of the design property, we want to make some ordered materials with a lot of function group in the port, then all the mercury can easily access and can be captured by our material. So also, we're also inspired by the metal protein. They're very flexible. They can, intermolecular cooperate to chelate the mercury. So this is what we designed. We use the simple soft-to-soft interaction using some thiol group and thiol ethyl group to incorporate into our material. We have a thionyl and a thiol ethyl. They can have the intermolecular cooperation. Then this is the material 1 gram of the material can absorb over 1,300 milligrams of the mercury. It's very, very good. And also we can reduce the residue concentration below 0.1 ppb. Basically, it's almost beyond the detection of the ICP mass. And of course, we also have extremely high affinities like some of the metalloprotein. The kinetics also is very high. So then we think about this flexibility really matters. Like a lot of metalloprotein, they're flexible. Then we also increase the rigidity and also eliminated incorporative. I found out this indeed matters, okay. And our material can be recycled and also can absorb all the heavy metals, lead, copper, and cadmium. And in addition, it can also absorb, the mercury vapor, which is 30 times the capacity of the active carbon current used, for the mercury vapor removal in the power plant. So in addition to this, okay, we can efficiently remove the contaminant using our function material. How about recover some of the precious metal? Yeah, this is the data I supplied, okay, a couple of weeks ago. So I just checked the market price today, okay. It's increased a little bit, particularly, for the gold and also for the palladium. Used to be platinum is more expensive than palladium, but palladium now is more expensive. We know precious metals are very important, closely related to our daily life. So a lot of applications is automobile. We need to use the precious metal as a catalyst for the converter. And also, they also use for the microelectronics. So the thing is, for the ores, though, the sources is very limited. And we also, there's some geopolitical risk, particularly for the palladium. Why now the price is so high? It's because of Russia, okay, the war in Ukraine, the Russia war. The palladium price surpassed the platinum. So why not we can use a different route? We just use, to recover from the microelectronics and also from the spin catalyst, which can save us a lot of, reduce the risk. So then we can design this, palladium nanotrap to efficiently and effectively, extract, recover the palladium from the spent catalyst, also from the microelectronics. So this is the part we designed. It's very simple. Actually, it's the polyvinyl polystyrene type of polymer. We just put some function group, pyridine group, amino group, and we can tune the capacity. This kind of polymer is widely used. Okay, we found that the capacity is very high. It's over 700 milligram per gram. And also, we can start from about 10 ppm, and we can reduce to less than 0.1 ppb. That means the recovery efficiency is extremely high. It's 99.99%. We can efficiently recover the precious metal. Of course, yeah, this type of materials can be easily recycled. We just do a simple filtration, and then we have the evolution solution. The residual concentration for the palladium for these two, they're different. Okay, this one is 0.1 ppb. That means the recovery efficiency, I said, is more than 99.99%. Of course, yeah. In the e-waste, we call it, okay, electronic waste. The pH is not neutral. We need to test the different pH. And in both acidic and the base condition, the recovery efficiency is more than 99.9%. Okay, in addition to this, of course, we always know in the e-waste, there's a mixture of different metals, particularly some other metals, iron, and nickel, cadmium, etc. And found for our materials, this material is not really good, but for this pulp, with amino and also position, it can still do a very good job, where in the presence of so many competing ions, they can still remove the, recover the palladium from 5 ppm to less than around 1 ppb. That means the recovery efficiency is still more than 99.9%. So in addition to, palladium used to be more expensive than gold. Now, when the gold is very expensive, it's even more expensive than platinum. So how about gold recovery? We can also design a pulp material. We can just use the sunlight to install some hooks, to our material, porous material. Then we can chelate the gold. So this shows, our material can be recycled. It's very, very selective. We can just select it to recover gold from the e-waste. Also, we did some tests. We just dissolved a CPU. Okay, we bought it from Intel. It's from eBay. Okay, my student then dissolved it, and then we can get this 24K gold. It's very efficient. Also, we estimated the cost. Okay, using our material, the recovered gold cost is less than $10 per ounce. Our material, so it's very, very cheap. So, okay. In addition to the recovery, I said there are a lot of resources, metal resources in the ocean, also in the brine. Actually, we can mine the ocean. Okay, some of the metals already industrialized, like sodium, magnesium, calcium, potassium. Also, lithium extract from ocean tested before, but it failed. Okay, because the efficiency was very low. Also, I think Japanese, they tried to extract uranium for nuclear power plant, back in 1990s. So for nuclear energy. So also, this I just highlight a few useful metals in the ocean. Like lithium is 0.1 ppm, concentration is very low. For uranium, it's even lower. It's about 3 ppb. Of course, gadolinium is very important semiconductor material. It's even lower. So also gold. So if we want to extract those, useful metals from the ocean, that is the job of a chemist. We need to design a new ligand, new material, be very selective to get them out. Like I'm using the hook, okay, fish them out. So, okay. So also the salt lake, okay, Brian. There are a lot of minerals, particularly lithium, that we can get them out. So this just shows you some very famous salt lake worldwide. We know this, of course, in Utah, the Great Salt Lake, and this one is in Bolivia, also this Dead Sea, and also this one in beautiful one in Ukraine. So there are a lot of minerals, resources in those lakes. How to get them out efficiently using new type of materials, new type of technology. This is what we're trying to do. Of course, we're talking now about for the carbon CO2 emission reduction, right? One of the clean energy we can call is nuclear energy. They don't really emit too much CO2, but the thing how we can get the uranium. So ocean contains 4.5 billion tons of uranium, which is 1,000-fold on the land. If we just use the uranium from the ocean, it can allow uranium for the nuclear electricity can allow human beings to use for 20 to 30,000 years. Maybe by then, some of us may move to the Mars, right? I know Elon Musk is trying to do this now. But the problem is, concentration is really low. Also, there are a lot of competing ions, how we can get them out. So actually, a few years ago, about 10 years ago, the Nuclear Office of DOE has a project where we're talking about this. This can be supplied for centuries of energy, and also the price will be very stable. Also, it's environmentally benign. So then we need to think about how to design the material, how to install a hook in our material. Always, I said, in biology, there are a lot of metal proteins. They can have extremely high affinity to a specific metal, right? So this is what we're learning. They have, cooperative binding, also certain distance, and also the angle. So what we're trying to do, we install 2 hooks on this, phenol ring, and to adjust the distance and the angle. So this is the series pop we designed. We put the hooks there. Then we can, one of the headache for this uranium in the ocean is uranium cadmium. The competitor is vanadium. Vanadium is good, It's my friend Bernardi, he's vanadium. He also is Adorno Award in physics 2 years ago. So vanadium is a headache. It's competitor for uranium from the ocean. So how we can design this? We design these pops. We can have very high capacity. This is in the water. Also, we can compete. How much very high selectivity for uranium over the vanadium. Also, this type of pops you can easily recycle. You just use sodium carbonate to elute it. The uranium will be recovered, and the materials can be used again and again. So in addition to this, of course, we need to do the real seawater. The seawater is, we got it from Atlantic Ocean. It's not from Miami, South Beach. It's 2 hours away from. There shouldn't be any contamination, okay? Because when my students took a boat to get some tanks of the real seawater, and when we do the check, you can see after a few days we can get 8.4 milligram per gram. This is the best. So far, this is a benchmark material. If we can have material can extract the uranium over 5 milligram per gram, we can use it to produce so-called a yellow cake, okay, as a nuclear fuel. Okay, in addition to this, now we can use nuclear, to supply, clean electricity. Now this is what we know what's happening now. The lithium EV cars. This is some of the data. You can see the increase of lithium battery. It's mainly for EV cars. Also, the number of EV cars sold. It's going to keep increasing. So Then one of the things where the lithium can be from, ocean has the largest reserve. Also on the land, 76% of the lithium is actually from the brine. But the headache is how to get them out. It's mainly we need to separate the lithium and the magnesium because they are very similar, they're diagonal. They have similar chemical and physical property. They're all going to precipitate. So how to design this? So always we got inspired by biology. In biology, we have some unconducting channels, potassium, sodium, and the calcium, right? So we think about, can we design a lithium conducting ion membrane, then use it to extract the lithium from the brine. Then we use some chemistry, basic chemistry, the oligomer ethyl, so install in our material, then we can have very good selective for lithium. For the transmission rate, potassium is the fastest, okay? And then we can reverse it. Lithium is the best, then followed by potassium, sodium, calcium, and magnesium. And we can separate them. Also, we made a device where we can achieve a selectivity over 70%, lithium and magnesium selectivity. So this is our recent work. Okay, we can further tune, the lithium and magnesium selectivity, and now we can reach over 1,000. This is a paper going to come out next week. This is a new benchmark. Okay, with this, I hope I can convince you, using this type of porous materials, we can not only do the pollutant, removal, we can also recover the precious metal, and also now we can use it for metal source extraction from water. So, and of course, all of the space in our porous material is nano-size, and the potential is endless. I'd like to thank my group members, former, current, former, all the funding support. Of course, I'd like to thank Pam for the nomination, also TAMEST for this prize. Also, last, I'd like to thank my family. Thank you. Hope with our material we can provide a clean and a sustainable environment for us and for our future generation. And thank you very much.
Thank you. That was incredible. The world needs chemists, right? We have time for a couple questions.
Hi. Oh, here. So you get these electronic units, and you're going to extract metals from them, so you need a solvent to do it. And so is that a limiting factor, or does that increase? I mean, what do you do with the waste after you've put it into solution and such?
Which metal you are?
Well, from like your electronic,
Oh, you mean e-waste?
Yeah.
E-waste, so we, one thing we want to extract the precious metal. Yeah. Then the waste, we need to find a way to treat them. We also have some way, I didn't talk about it. We do can use our material. We talk about in the first part to remove all the heavy metal. That we can have so-called build a Titan column. First of all, we get the useful, precious metal out. Then the rest we can use our material, other type of materials, to remove all the contaminants. Then we have a clean water. So.
Please.
Yes, excellent talk. Congratulations again. I'd like to get your comments. Most of the metals, or at least copper, those are organic complex with natural organic matter in the real environment. Do you face any problem? And second is gold. Normally cyanide is used to extract from the mining. And how far you are from really extract the gold, that will really solve the problem, because cyanide is really nasty. Thank you.
Yes, for the copper depends, copper, actually, we need some in the body. So what I'm talking about for the copper removal, heavy metal is mainly from the chemical industry, the high concentration. We cannot discharge a high concentration of the copper metal to the environment. This has got to be removed. For the gold, it's indeed for the e-waste. So far, the best one is using cyanide, and what we are trying to use is concentrated nitric acid and the sulfuric acid to dissolve it, then we extract it. And also, I didn't show the details, because of the time limit. we use our material to get the gold, and then we use the solo just to precipitate to go from gold straight to gold zero. Directly, we produce the 24K gold. That's what I just showed. In the real environment, also we did the real underground water with some gold in Texas. My students get some sample, water sample. We can extract some gold from the underground water. The gold from them, the water.
Yes, in South Texas, I learned that there's uranium there in some water. So I think this would be good to solve some problems.
Yeah, the uranium, we can do very, very good job. We can reduce the uranium to less than 0.1 ppb. Basically, it's undetectable. That's the detection limit for ICP mass. I didn't talk about the other part. In parallel with the uranium extract from the ocean, that's one of the projects by DOE a few years ago. Now the DOE interest is to recover the spent fuel, because there's still about 30 to 40% of uranium can be used from the spent fuel. That need to be recovered. Our material can also recover those uranium from the spent fuel because they're very, very robust with very high radiation stability. We did some tests using the gamma ray and the beta ray to radiate.
Okay, unfortunately, the time is over. Let's congratulate Dr. Ma one more time.
Thank you.